My talk will be a little bit lighthearted. I will focus a little bit on the applied side, and I will sort of discuss how to do time series forecasting using machine learning. A little bit of background, and yeah, dinosaurs. Why dinosaurs? The reason is that for the past 10 years or even a little bit more, I have been working with those large traditional enterprises, doing a lot of things around analytics and machine learning. And to me, those big enterprises are a little bit like dinosaurs. You know, they are very big, they are very powerful in terms of resources that they have, but at the same time, they are a little bit, I would say, old-fashioned and not always sort of following the latest developments. So artificial intelligence and machine learning for those dinosaurs are a little bit technologies which are not fully in their comfort zone. Having said that, what I'm seeing recently is that adoption of machine learning solutions is accelerating very fast. And I do feel that there are a lot of opportunities where machine learning can really help in doing traditional business. And today, during the talk, I will try to give you one example of what we managed to achieve. Why forecasting matters for Circle K? Circle K, you probably know the company. What we are doing, we are selling fuel. Relatively simple business, you may think. What is important for us is to make sure that the fuel is available where our customers want to buy it. So we want to know how much we will sell and when. The reason why we want to know it is that we want to be able to forecast the demand to plan our supply operations. And delivering fuel is actually quite a complex business. You need those trucks like the one on the picture. It's very expensive to send them, first of all. And secondly, considering our scale, we have over 1,200 stores. It's a big logistic operation to make sure that the fuel is delivered from terminals to our stores. Pretty much every day we have more than 1,000 trucks delivering fuel all over the world. So by having accurate forecasts, we are able to be more efficient in our operations planning, and then obviously helps the business tremendously. Time series forecasting, just for my understanding, who here had experience in the past with time series forecasting? Can you please raise your hand? Okay, half of the group, great. So time series forecasting, I would say it's a very well-researched area of statistics. If you Google a little bit and you are new to time series forecasting, you will probably stumble upon ARIMA. And ARIMA is one of the, I would say, state-of-the-art statistical models to do time series forecasting. If you want to use it, there are a couple of steps. You need to take your observations over time. You need to make sure that they are stationary, so you will do differentiating of the mean, so essentially the trend. You will differentiate the variance. Then you will look at the seasonality. You need to say whether the seasonality is multiplicative or additive. You will look at autocorrelation. You will decide whether to use autoregressive or moving average terms. And then you will look at the residuals and see whether you have any predicting information left, and you will try to squeeze it over and over again. Relatively complex process, to be honest, if you want to do it well. The outcome of this process is what you see on the picture. You have your historical observations, and you want to forecast the future ones. And this result is actually quite good if you look at it. There are, however, problems in practical applications. One problem here is you notice that ARIMA managed to forecast those spikes. Those spikes are associated with holidays. During holidays, obviously, the demand doesn't act normally. And it's fine if those holidays follow the seasonality that you've included in your model. But it's somewhat problematic if the holidays are moving holidays. For instance, Easter holidays, they don't happen at the same time during the year. So you may sort of want to sort of factor it in and do a little bit more complex modeling. But when we sort of tried to do it, we sort of thought, you know, we cannot be the first ones who try to solve it, right? Someone must have done this in the past. So we encountered Prophet. Prophet is a time series forecasting library released by Facebook. They published a research paper just last year around Prophet. And the main goal of Prophet is to make it easy to forecast common business time series. Prophet, it essentially does a couple of things. It's estimating your trend using linear or logistic regression. And what's more, it's piecewise, and that's important. I'll mention in a second why. You're able to fit your yearly seasonalities, weekly seasonalities, and also hourly seasonalities if you're forecasting on intraday level. You are able to provide a list of holidays, and those holidays, effect of those holidays will be assessed and included in your forecasts. Behind the scenes, Forecast uses Stan, a probabilistic language, programming language that Stan exposes. But it's really, I would say, very easy to use. It will give you a couple of nice things, like, for instance, saturation. So you make sure that you don't forecast you will have more users than people living on the Earth. It gives you very nice features around intraday forecasting. You can set sensitivity when it comes to trend change points. So you can say, and you can a little bit play with the forecasting parameters there. So with that, we had really, really good experience with it, and the results we were getting were quite okay. But you may think that it's easy, right? So you find the library, just start using it, and you're done. In reality, that's not the case. This is a chart which shows sales of our one of our fuels over a period of couple of years. And actually, this product was sold under a couple of different product codes. Reason is that you will very rarely see in an enterprise environment that one product is sold for 5 or 10 years. It will change because of you will have different styles. You will have, if you say, for instance, cloud, you will have different styles. In our case, we were sort of changing the grade of the fuel because of all the regulations around biofuels. We were introducing additional, I would say, additives to the fuels. So we needed to identify over the historical period and merge the history into one continuous time series we could use for forecasting. How to do it? The method that we have used is called dynamic time warping. And dynamic time warping and goal of dynamic time warping is essentially to measure similarity between time series. And measuring similarity between time series may seem like a simple problem. You just take 2 time series, you calculate the difference between each of the observations, and then you have some measure of similarity. In reality, there are challenges when it comes to partial matches. So you can have a different start point, different end point. You may be missing a piece in the middle. At the same time, the time series can be stretched, or it can be more narrow. Couple of examples here. You can see this is relatively easy to say whether those two are similar. If you look at this example, not so straightforward. Although the similarity metric would probably be reasonable, and it would show those 2 time series are similar in its nature. There's good research. It's quite dated. It's from 2008, Ding et al. But dynamic time warping can be used as a metric in clustering time series, and you will get relatively good results by doing that. From an applied side, why it is important, as I mentioned, you can identify similar time series. So essentially, if you have multiple products, you want to build a continuous history, that's a great use case. Another great use case is when you work in an enterprise environment, you have to consider what to do when you will introduce new products, when you open new stores, and you don't have a lot of sales history. Usually, you will go a little bit blind when trying to sell in those locations or to sell those products. But after a couple of days, you will have enough history, and you will try to match the history that you're observing with history from other locations or for different products. And again, having a good way to assess similarity is crucial there. One point to mention also, there's a big difference between the fact that a product was not sold or the product was not bought. An example, we do sell winter fuels, and those winter fuels are only sold during a particular time of year. If we were to sort of, we had no understanding of what we are forecasting, we can say, oh, it wasn't sold during the summer, maybe we should use for some replacement products, maybe we should sort of imputate the data somehow, but it just really wouldn't make sense from like a business point of view. So having someone who will validate your assumptions and your modeling is actually crucial to being successful. Then data availability. So once you start doing all of the work around the data you are using for building your machine learning models, it is really important to, I would say, treat those data pipelines separately from your machine learning pipelines. The reason is that the data pipelines that you build and the data sets that you create, you will use them over and over again, the more sort of machine learning use cases you find. If you sort of build a one system which has all the sort of data pipelines and machine learning integrated, it will be very hard to reuse afterwards. if you work in a company which is having some sort of a data lake or like a data warehouse, you're very fortunate. If not, I think it's worth building something like this for your machine learning use cases. And a data lake is really a very logical concept. It's essentially like a water reservoir, but instead of water, you have just data that you just pipe in there. Whatever you gather, you just pipe in there, and you need to have ability to just retrieve it afterwards. Technology-wise, doesn't really matter. You can use a big drive if you want to. You can use some horizontal scalable storage solution. You can use a Hadoop cluster. It doesn't really matter, but just make sure that whatever data you are using, you store it and you are able to leverage it later on. Are we done? We found an algorithm. We've sorted out our historical data. We are storing it for further use. Not quite yet. There are many more factors that are impacting fuel demand that when we sort of started to think about it, things like local events. If there's like a sports game, people will usually take their car and go there. Things like advertising campaigns or price promotions, they impact our customer traffic heavily. Weather conditions, and weather is actually a funny one because it's not only weather at the station, but it's also weather in the travel destinations, so the weather in the places that people go to. But at the same time, those are also weather forecasts, because you will make your decision whether you go to the seaside based on the forecast you see on Thursday, and then you say, oh, over the weekend I'll go to the seaside or to the Lake District. What the weather actually will be, maybe it doesn't have such big of an impact. And there are other factors impacting demand, and what we sort of started to realize is that trying to extensively model it will be too complex for us. And by complexity, I mean it's not maybe complex, but it's time-consuming to do it right. So, we had this expression on our faces, right? We are doomed. There's nothing else we can do to improve what we're doing. But actually, as with kids, after 15 seconds, you start thinking, okay, so what we should do? And then we sort of figure out, yeah, machine learning, that might be a good application. Machine learning should be good at taking huge amounts of data, understanding what's the relationship between the variable you are trying to predict and the variables you are using to predict it. Yeah, and that's probably the weirdest personification of machine learning you've seen, but I sort of like this picture, so it's here. But what we sort of decided is we will use machine learning to do time series forecasting, and we've done it in a little bit different way because there are machine learning models tailored for doing time series forecasting, right? Recurrent neural networks, LTSMs, but to some extent they will all suffer from the pitfalls that statistical models suffer, that they are not able to look at a lot of those, I would say, external factors and assess their impact. So what we wanted to do with machine learning is that we wanted to take the forecasts that we already created, those statistical forecasts, which are actually not so bad all in all, and use machine learning to have a better understanding of how particular events impact those promotions and how those events can be used to improve accuracy. So what we have done, we have first of all modeled the time series data into like observations. A time series, it's temporal data. Machine learning models have no understanding of the structure of the data they are dealing with, so we need to model it somehow. So we did model the temporal characteristics of time series into observations. We included the time series forecast, and we did run a couple of models as some of the predictors. And then obviously all the features like weather and so on that I was mentioning previously. One more mention here, and that's something that we had quite a few discussions with our business partners as well who are working on this project is, you are only able to forecast based on what you know and what you will know at the time of forecasting. Therefore, data leakage is something that you really have to pay attention to. Because our sort of business partners, they said, okay, the price of fuel for sure is impacting customer purchasing decisions, right? So it's impacting demand. At the same time, we knew what the prices of fuel were historically, and we were sort of tempted to try to forecast what the price of fuel will be in 3 days' time. If you are able to forecast what the oil price will be in 3 days' time, you should be in a completely different business, right? You should be running a hedge fund and you would be very well off. So essentially, you need to be very aware of leaking data. Also, when you sort of model the temporal characteristics, that's something that can happen quite easily. there. So we have our data. Data is cleaned. We've modeled our features for using machine learning. So what's the next step? Next step is around measuring results. And when it comes to measuring results, you have a lot of, I would say, traditional ways of measuring accuracy of time series predictions. You have things like mean error, mean absolute error. You have relative error metrics. You can look at R-squared, so see how your model explains variance in the observations you are looking at. But really the takeaway that I wanted to share with you is to measure what you are trying to solve and measure what really matters to solve the underlying problem. And in our case, where we worked with our supply team and the analyst team there, what they really cared about is the variance of forecast for individual stations. And what I mean by that, they wanted to make sure that if you look at the variance, so what's the error for individual stations, they wanted for it to be really predictable. They wanted it to fall from like between -10 to 10% so that they can run the supply operation with a certain amount of confidence. And there will be obviously outliers always because there's a car accident and people are driving to the station. That's not something you are able to predict. But for a lot of the cases, they just wanted to have a certain level of confidence. And sort of this also illustrates some of the results we were getting. Those were the results we were getting from using like a legacy forecasting model. It was just based on exponential time smoothing. Those were the results that we were getting from a machine learning model that we deployed. So as you can see, the errors are mostly between -10 to 10, -15 to 10%. Using legacy forecasting methods, it was like all over the place. So it was like -50 to 50. So it means that when you planned your shipping plan and your deliveries to the stations, you sort of had to assume that it can be 50% more or less than your forecast is showing you. So not something that you can really use to run a business. Next step is, and one of the lessons learned for us and experience I wanted to share is, it's very good to think about a machine learning framework. If you are trying to solve a machine learning problem, very rarely you will need to code the algorithm yourself, right? Even if you do image recognition, you would probably start with TensorFlow, you would look at Google Object Detection, let's say, you will take some of the models that are implemented there, then you would probably modify a couple of layers and create your own models by customizing those models, and only if you sort of are missing features and functionalities, you would create something on your own. So that's one of the reasons why a machine learning framework will be helpful is it gives you an out-of-the-box method which you can easily and quickly apply and sort of see whether you are getting the results you are hoping for. Second reason is you will spend a lot of time fine-tuning your models, doing hyperparameter tuning, and majority of the frameworks will essentially give you a very good interface to do model tuning and model scoring. But maybe most important use case is that at some point, if you work on big problems, you will run out of either computing power to train models, to run predictions, or you will run out of memory to actually fit data into like individual machines. And if you go for a framework like Spark machine learning, we used H2O, you are able to scale that framework horizontally. So if your data volume grows, you can just add machines to your cluster. You can take your data directly from your data lakes or your Hadoop cluster, for example, and all of the sort of scoring happens on your, let's say, ML cluster, and you don't need to have a powerful laptop. Your laptop can be, a toy or a mobile phone if you want to, and you are able to train powerful models using that. Next step that we sort of found, and this is like an interesting learning I wanted to share as well. Very often you think, and usually it's right to say, that more data will give you better results. When we started to evaluate our models, we found it's not necessarily the case. We tried one of the experiments. We were testing how much the amount of historical data is helping improve results. And actually, we were getting best results where we used only 2 years of historical data to train models and to build those predictions. When we started to use data which is older than 2 years, the performance did not improve. What's more, in some cases, it did decline. The reason being that if you use data from 2010 or 2011 to train a machine learning model, it's very likely that the environment, in our case, the business environment and the field business, did change over the span of 8 years. So data from 2010 is no longer relevant. So if you build your models, more data is good, but only more relevant data is good. And selecting relevant data set is also something that should be data-driven. And I would recommend running experiments on whether it helps or not. In our case, it definitely helped. Moving next. Feature importance. Feature importance is an interesting one. Personally, I'm not a big fan of looking at feature importance and assessing the results you are getting and trying to handpick features. Most of the, I would say, even the machine learning models that are quite modest, traditional ones, will be able to do feature importance analysis on their own. Deep learning, obviously, will do it as well, and all the neural networks. But we had a lot of, I would say, value from feature importance, and that value was around helping to build trust and engagement with users of those machine learning models. If you are deploying a machine learning solution in an enterprise, it will be used to make decisions, right? There will be always someone who will take outputs of your model, and he will make some decisions for which he will be responsible for, right? In our case, ordering a couple of thousand cubic meters of fuel to be delivered to a terminal, quite an expensive operation, sending a couple of hundred trucks to deliver fuels to the stations. That person will really need to trust in your models. And discussing feature importance with our business partners was something that was, I would say, helping build that confidence in the solutions we are creating. This example, it's an interesting example. It was an example from when we sort of deployed those models in Sweden. And one of the most important features was the calendar day of month. And that was like absolutely ridiculous for us. Why the day of month matters so much. But when we started to discuss with analysts, apparently everyone in Sweden is paid on the 25th day of the month. So the payday impact is massive because people get their money, they go doing shopping, they fill their cars, all the shops are filling up with inventory, so also the heavy trucks are delivering inventory and they are filling up more. So it was like the entire economic cycle, like the microcycle, was based around the payday effect. And it was actually an interesting discussion, but they were the analysts that sort of looked at it were very, to some extent also surprised, but they had a feeling that this has a big impact on the supply that they are seeing. Next, local explainability. Won't cover this in many details probably, but if you use machine learning models, very often those will be black boxes. Using packages like Lime will definitely help to understand individual predictions. In this case, it's some demand prediction. It was a prediction for week number 40, usually a little bit less sales on that week. At the same time, previous weeks, we've seen more sales, which was a positive contribution. Quite interesting to look at if an analyst wants to deep dive into why a certain prediction is made. At the same time, I would say it's not so trivial to get a good fit. And usually, you will need to spend a little bit of time to make sure that your explainability makes sense, and it will never be 100% accurate. There will be always this black box element that you will not be able to explain. PDP plots, yeah, also helpful if you want to look at individual variables and how they contribute. Overall, this is the outcome that we've got. We've reached 98% level of accuracy that was required for running the supply operations. It doesn't mean it was 98% accurate. It means that the confidence boundaries within which our sales and operations team required for the forecast to fit, we were managed to fit in between those. It's a nice chart, and this chart shows the bars are actually the actual sales. It's just an example from one station for one product. The red line, or like the reddish line, it's the best, I would say, model we managed to fit using statistical methods. And it's actually quite a good model because it's sort of following it's able to identify the peak, the demand is increasing, but then you sort of see the machine learning model, which is actually better because it was able to identify the morning peak, and then obviously not so much going on, and then the afternoon peak. This doesn't have, I would say, any predictive, any scientific value, but it's just interesting to look at a couple of examples to see that the error metrics that you are seeing that are better actually translate to results which make more sense from a human perspective. And then I guess the question: are we done? And why I have those two pictures? when you build your machine learning solutions, you can end up like this, or you can end up like this. And what's the difference, and how to avoid ending up like this? And I think that it's sort of a lot around automation. Because if you create your code and you are trying to sort of do it everything as a one block of code. You are trying to combine your data pipelines with your machine learning pipelines. And you end up with this sort of ugly creature that you need to sort of retrain every so often, and you get a lot of questions that people will ask you, oh, why I got this prediction, and I was expecting something else, and you need to deep dive. That will essentially take a lot of your time, and you will create one machine learning solution in your life, and you will be stuck supporting it until the end of your days. And automation is really what allows you to focus on other things once you've done something. What's important when it comes to automation, you will iterate endlessly. Even if you have a model deployed to production, you will start working on new data points, so potential data points which may have predicting power. You will try fine-tune your algorithms. There will be a new algorithm or a new research paper that you would like to test. So it's very important to automate evaluation of the models, have a champion model, and evaluate new models against the champion model and a benchmark model. Make this part of your workflow of code versioning and releases, so it's actually available and versioned in your Git repo. Separating data and machine learning pieces, that's something I mentioned. Automate deployment, at least to the pre-prod. In reality, whenever we deploy new models, we ask analysts to actually look at the results and say whether those results are acceptable. We don't have fully automated deployments to a production environment, but you should try to automate at least deployments to pre-production so that you are not worried about sort of building the code yourself. And also, I think that one of the most important points is when you build machine learning models, you will have code which prepares your data, right? You will have code which does the logic of evaluating results. It's extremely important to make sure that you use the same code during training and online predictions. First reason is that you have to write your tests only once. Second reason is you will always use the same. There will be no cases where you trained model in a slightly different way that you are actually predicting using that model. And that's something that we sort of converged to this because we had issues, right? We started from two separate blocks of codes. That code was quite similar, to be honest, but still, we did it separately. And it was like a massive time eater for us. So we did decide to merge it, and it was definitely the right choice. On the automation and maybe on the orchestration side, one of the tools which is worth looking at is Airflow. Airflow is a tool which was, I think, created by Airbnb. They've open sourced it, and I think it's in Apache incubation stage right now. But Airflow is based around acyclic graphs, directed acyclic graphs, and you define the logic of your workflow in Python code. So you can say that I want to have a certain data task run, or maybe run a data query, then you want to do something on your command line, then you want to run some model training, you want to iterate. It's actually quite powerful to automate and orchestrate your workflows there. 2 points which I'm not covering in this presentation. One is around integration. Integration in the sense that you need to make your results available to the end users and to the systems which will actually run the distribution. Second, to present results. I'm not covering this because we have used commercial tools for that. Having said that, you could easily do it writing some code to do integrations, and I know sending data to an SFTP, invoking an API, whatever, depending on your infrastructure setup. Results presentation, if you're an R user, you could build like a Shiny app, you could build custom applications using like React framework, whatever it's interesting for you and the tools you have available. And then I think the last slide for me, couple of points. When you start your, I would say, journey, because it will be a journey in deploying machine learning models, think about what's your business sufficiency level. Because you can always try to improve your model. You will always find new data points that you may try. You will always may sort of do a slightly better hyperparameter tuning. But you will do it endlessly. So try to have a good baseline of what you are aiming for. And we have sort of found it. We've reached a certain level we are happy with, and we have ideas how to improve it, but we are not pursuing those. We are doing different projects right now. Secondly, it's worth clarifying with your business users that machine learning is never 100% accurate. In the same way as humans are not 100% accurate. Why this is important? Because if you work with like an ERP system, right? You develop a system to do accounting, for example. And people expect that this accounting system is always right, that it adds all the numbers and it never makes mistakes. And with machine learning, it's not the case. Machine learning would look at 100 of pictures. It will say that on 98 of the pictures, there's an object and it will recognize it right. But on 2%, it will guess it wrong. It will get it wrong, just as a human would. It's not traditional IT when you do machine learning, and people somewhat expect it is. So clarify the expectations at the very beginning. And also, in a corporate setting, you will have a lot of various opportunities to apply machine learning. Some of them are really good in terms that you will have the data required, and the problem will be, I would say, solvable with the resources you have. In other cases, you will look at those problems and you will notice that, well, the results you are getting after initial couple of weeks of doing like a proof of concept are not the results that you will really reach the business sufficiency level within a reasonable amount of effort. So I would say be very conscious, and if something doesn't work, either change your approach dramatically, try something very different, or just abandon the idea and come back to it after a while, because you will spin your wheels and you will not get the results you are hoping for. To end, this entire sort of demand forecasting using machine learning, to get results which were good and to run a proof of concept, it took us probably 2 to 3 weeks. To productionalize it with all the automations, with all the automated deployments, probably 8 to 12 months. So quite a bit of time. Having said that, right now it's pretty much hands-off in terms of the time we spend on looking at those models and fine-tuning them is close to zero. It's a solution that just works. And that's it.